I'm just glad there's not a license above extra. I don't even begin to imagine. Well, I mean, I know there is, but as far as for me, it's.
Well, I guess the only thing would be a commercial license.
Yeah, there's nothing in the amateur license.
Right, it's wonderful.
Well, you can take another test, open book, and be a VE.
Oh. Well, I won't.
Yeah.
I mean, it's open book, I think that would be good.
Well, it's like most open books, it's not easy. You have to, the answers aren't written out in the manual. You have to read between the lines on a lot of them. But I don't know what it takes to pass. I don't know anybody that hasn't passed it. You just have to do your application and fill out the 20 or 30 questions and send it in. And they send you a little tag. And you're good to go.
So you don't know anyone who has failed it.
Right.
John was happy.
Okay. There's a lot of calculators you can find online, which will let you do some of the Smith chart calculations, like simple matching networks, where you put in the parameters and it'll give you the answer and it plots things on the Smith chart like you were doing it graphically. But I looked at some, they don't do more of the complicated stuff. So basically, the Smith chart came about by this guy, Philip something Smith, who I think was a Bell Labs guy. And he developed it to help in solving transmission line problems. So it turned out to be a much better tool than just plotting stuff on rectangular coordinates. Remember when we did that and we plotted the real and imaginary? Well, he took that, and if you extend the real axis from 0 to infinity, and you draw it as a physical length line, and you say, I want the middle to be 1. So I go 0 to 1 to infinity. I can have whatever scale I want, right? It's kind of logarithmic. Then he said, well, I'll extend the imaginary axes to infinity. So I have a plus j infinity and minus j infinity. So I guess in mathematics, infinity is infinity is infinity. So they all meet at one point. So if the real infinity is over here, and these are there, but they're the same point, and then it wraps around and makes a circle. Well, that's all he did, was curve the reactance axis, which is the vertical, so that all those points meet at infinity out at the end. And then any line that would have been parallel to the real axis now becomes a curve going back to infinity. And any vertical line along the real axis now becomes a circle back where its reference point is at infinity. And that's how you make a Smith chart. Well, it turns out it's very useful because you can easily plot real and reactance of something. And then, well, the first thing you do, because of the 1, is you normalize your numbers. So if you wanted to do things based on 50 ohms, you divide all your measurements by 50. So a 50 ohm resistance would be plotted as 1 on the real axis. It would say 50 plus J50, then it'd be 1 and J1 wherever that reactance line was. So when you plot that point, say it's for your antenna, if you draw a circle based on the center point of 1, that's called an SWR circle. So every point on that circle is going to have the same SWR. So you see all these different, and it's going to be resonant at 2 points where it crosses the real axis. The SWR is going to be whatever that distance is. So, and then they decided you can take the outside of that circle. So you're going from 0 on one end, which is a short, right? Low impedance. If you go around to infinity, that's a quarter wavelength. So if you want to find out what the reactance is on any length of that coax other than a quarter, how far you go around, it's going to give you that. And the direction that you go, which they label as to the generator and from the generator, I think, determines whether it's inductive or capacitive. You can do all those kind of neat things with it. And it's real easy to do the stub stuff. You plot what your load is, and then you figure out based on and you have to do it graphically with lines, how long the stub needs to be and where to put it. Those things are, once you learn how to use it, fairly easy. So the main thing is that the horizontal axis or the resistance axis is going to go from 0 to infinity, 1 in the middle, and it'll normally be the horizontal line. One of the things they changed in this question pool is their example figures were all rotated 90 degrees and the resistance axis was vertical. Nobody does a Smith chart like that. So they finally fixed that. And then the vertical or reactance axis is going to go from 0, where it crosses the real, to plus and minus infinity. And also on that outer circle, it also means that the resistance is 0 on that circle. So there's their modified diagram like it should have been. And this is a very simplified Smith chart. If you go buy one, a printed one, it'll also have admittance arcs on it and conductance. So it's got a set of circles and arcs going in the opposite direction, because sometimes it's easier to solve a problem by converting it to admittance than it is to impedance. So the resistance circles, okay, give you constant resistance, normalized resistance. So here, the 1 would typically be the 50 ohm circle. So any point on that line is going to be 50 ohms. And the reactance arcs are all the same reactance. So this one would be 50 ohms of inductive reactance or 50 ohms of capacitive reactance. And any point on this horizontal line is going to be a pure resistance. So what type of coordinate system is used in a Smith chart? Bravo? All right. Circles and arcs. What are the two families of circles and arcs that make up a Smith chart? Charlie. On the Smith chart in 9.3, what is the only straight line?
Yeah.
The arcs represent constant reactance, and the outer circle is the reactance axis because we just proved it. Right? So when the resistance axis is horizontal, like in this picture, like it's supposed to be, positive reactances or inductive are plotted on the upper half, and negative or capacitive is plotted on the lower half of the circle. So what do the arcs on a Smith chart represent? Delta. Let's see, on E9G, the name for the large outer circle on which the reactance arcs terminate. Did I hear a bravo? Right. It's an axis even though it's curved.
You know what you talking?
The large outer circle, this one. That's the reactance axis. Remember, if we hadn't curved it, it would be vertical. And like I said, it uses normalized resistance. So it makes it easy. You just divide everything by your 50 ohms or whatever you're working with and plot it. And then when you get done, you have to unnormalize it. So you multiply. That center point of 1.0, they call the prime center. And then the definition for normalization is just reassigning the impedance values with regard to the prime center. So it's relative to that one reference point. So you're basically saying I'm 50 ohms and my reference point is 1. So that's how I plot everything. How is a Smith chart normalized?
Charlie?
What was that?
Is it Charlie?
Any others? Amy's right again.
Yeah, I was gonna say Charlie, like I knew she was right, but I just thought I'd be honest about it.
You figured you'd let somebody else have them.
Yeah, she's got all of
Figured
it.
you'd get them.
Yeah, it's correct.
That's about.
One of the things they're used for is to calculate the impedance along a transmission line. Like I said, this outer circle outside of the reactance arc, you'll see, which you can't really read here, but it's plotted in fractions of a wavelength. And it goes, and there's two of them, one in one direction, one in the other. So that determines whether you're doing inductive or capacitive. And you can also calculate the SWR, like I mentioned, when you plot, like this point here was impedance of 0.5 plus J1. So it was 25 ohms and 50 ohms inductive reactance. So that's why it plotted up here. And when you draw that circle, that's the SWR circle. And if you look at where it crosses, I can't read it, but that would be a constant SWR for any point on that circle. It's going to have the same SWR reading. And that's one of the things that you often add is the SWR circles. Sometimes you'll also see these little charts at the bottom. So in some of the calculations, you draw vertical lines down and see where that intersects, and it gives you some other parameters that you can figure. It turns out they're extremely versatile. And this Mr. Smith puts out a hardback book about that thick and about that big, just on how to use it. Which of the following can be calculated using a Smith chart?
Yeah,
What did you say? Oh, okay. I thought you said delta. My hearing's not too good. The echoes in here make it worse. Yeah, impedance along transmission lines. That's the easiest thing to do with it. Which of the following is determined, often determined, using a Smith chart?
sure. Yeah, sure.
What third family of circles is often added to a Smith chart during the process of designing impedance matching networks? Whoops, I double clicked. What's the answer to this one? Did I back up?
You did back up.
Yeah.
Oh, okay. Another common application is to figure the length and position of a stub. And we're not going to go into how to do that. You kind of calculate it and you come up with the electrical length for the stub and the electrical position. And then you have to apply the velocity factor to find out the physical lengths to go along with it. Which of the following is a common use for a Smith chart?
I believe that it's start. Oh, was the E9G answer?
Now you're going to have to do it on your own. Amy's not here.
I know. We can wait.
That's anything was said.
Huh?
Yeah. But I should have gone with Jim. Sneak it out, Jim.
You can figure the length and position. In what units are the wavelength scales on a Smith chart calibrated? I told you, if you listened.
Yeah, Jim.
What's
I'll
not,
give you a hint.
it's not seared.
In one direction, it's 0 on up to 0.25.
So,
So,
Fractions and transmission line electrical. That person?
yeah. Oh, my goodness.
Well, that wasn't painful.
No. This has been like just a breeze today. It is Lord.
Yeah, we got one more.
You're seeing it for acids.